All right, so far we have sort of discussed the idea that light is a wiggle in this sort of invisible ocean that surrounds us of something called the electromagnetic field. And the reason why this took so long to figure out is because this weird electromagnetic field, it only interacts with humans in a very few interesting ways. So we kind of didn't notice it. We just kind of expected that was normal, and we never even thought to look for it until we started to be able to sort of test the world with things beyond our own senses, with machines and equipment that could be more specific and more accurate and more detailed. So light is a wiggle in the electromagnetic field. Well then, how do you make these wiggles? How do you make wiggles? How do we make them? How does nature do them? Because obviously, if I wave my hand around, it doesn't make light. So when I wave my hand around, it doesn't seem to make any ripples or wiggles in the electromagnetic field. If I wave my hand in the water, it makes water waves. So there's something weird about this field, because only certain things can make it wiggle. And that's what we're about to find out. And it's actually quite simple. The electromagnetic field can be made to wiggle or to vibrate. I'm going to use the word vibrate. We've been using the word wiggle as we've learned, but now I think we understand that the word vibrate means to shake around. So it can be made to vibrate by moving or wiggling charged particles. And maybe I should put here another word, not for anything that's going to confuse you right now, but as you learn more about the world and you study science, by moving electrically charged. Let's put that down, because there's actually different kinds of charge for different things that you'll learn about much later in your educational journey. By moving electrically charged particles around. So, to put that in sort of a picture form, like I said, if you take a cork and you have it resting in the water like this, and you push the cork with your finger, the water will begin, the cork, of course, will begin to vibrate up and down. So the cork will shake up and down as it bobs, right? It bobs, it floats and bobs. And of course, then little ripples begin to form in the water, and out they go. So we can make ripples in the ocean or in water by wiggling just about anything, any kind of matter. A log, a cork, your hand, a boat, it doesn't matter. But this does not make wiggles in the electromagnetic field, which is that sort of invisible ocean that surrounds us all and everything. The way you do that is you take a particle, instead of a cork, it has to be something that has a charge. So it could be a positive or a negative charge. Let me write that. So let's just say, usually, we're talking about electrons when we talk about electromagnetic radiation. So I'm going to put an E here with a negative charge. That's our sort of weird little picture we use for an electron. We don't know what they look like, but that tells us E for electron. And if you wiggle this electron around, if you can wiggle the electron up and down like this, it will make a wave in the electromagnetic field that will go out, just like the waves in the ocean. So that's how you make light. You wiggle electrons. You could also wiggle protons. You could also wiggle anything. You could wiggle an ion. You could wiggle a sodium ion, and that would also make wiggles in the electromagnetic field, but not a neutron. If you wiggle a neutron, nothing happens. If you take a neutron and you wiggle it up and down, just like waving your hand, the electromagnetic field stays flat. It does not wiggle. That's what's very peculiar about this electromagnetic field. It has to be shaken by a charged particle. That's why we call it the electromagnetic field. You have to have electric charge to shake it. So, how do we make light? Well, we make electrons jiggle and wiggle and vibrate around. And there's actually many different ways that you can do that. So, let's have a look at some of the different ways we can make electrons wiggle and jiggle. Well, the most obvious way when you think about electrons and electricity is you think about wires, right? So, if we have wires, here's a wire, and in this wire there are electrons, right, which can move through the wire because they are pushed by something called voltage. You remember that from grade 9. You did electricity and you learned about how voltage can push electrons through a wire. Now remember, a wire is not just an empty thing. A wire is made of copper atoms. So we have to remember, we draw all these pictures and it looks like there's just like a tube with electrons shooting through. Well, that's not really what's happening. What's happening is you've got a whole bunch of copper atoms that make up this wire. Copper atoms. And each of these copper atoms has electrons that buzz all around it, right? So I'm just going to draw a couple of wiggly, there's electrons here buzzing all around these copper atoms. Well, what voltage does is this. It causes an electron here to jump into the fray of buzzing electrons all around. But now there's one extra. There's one too many. And so it's like almost like in a crowded room. If somebody pushes their way into the door over here, on the other side of the room, somebody might get pushed out. So on the other side, the electron is pushed out. Because there's sort of like a bump, 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 push, push, push all the way along. So we say that the electrons are flowing through the copper wire, but in a sense, they're more or less just kind of bumping into the atoms and pushing electrons along like that. It's more of a domino effect, right? One pushing the other, than it is little electrons like this shooting through a tube. But we draw it that way for simplicity. We often do that. The danger is we forget what's really happening. And we start thinking in terms of all the simple things, and then we forget what's going on. Now, if you take electrons and you bump them through this wire, they will make ripples in the electromagnetic field because they are bumping along and moving. And so electricity or electric current makes light. Now, the problem is when you have a wire in your house, we don't see the light. Remember, light is not just the colors we see. It's also radio waves and X-rays and microwaves and all these other little ripples that we can't see. So what we've discovered by building machines that can detect all the kinds of light, we've discovered that humans can only detect a few of the kinds of light. So we didn't even know they existed until we built machines that could finally find them. So we can use electric machines that can sense the wiggles that are around a wire in your house. Your house, as the electricity goes through the wires in your house, it makes ripples in this little ocean, this electromagnetic ocean. And we can detect that. We can get a little meter and put it near a wire, and if electricity is turned on, the ripples coming off the wire will affect the meter and make the meter wiggle and show us that there is wiggles there. There are wiggles there. So electric current can produce light. Now, usually electric current produces light that's not the kind we can see. So we don't notice it, but it's there. We can also make electricity do work for us. So watch this. we can get electrons like this to push their way through a wire. And then we can put another substance here. Like, you know, in a light bulb, you have the little filament, the little bit of, it looks like a little windy, spirally wire, but it's not actually made of the same kind of metal. It's not copper. It's made of something called tungsten. And so those tungsten, W is the symbol for tungsten on the periodic table. Those tungsten atoms, they hold on to their electrons a little differently than copper. Copper doesn't mind. You see, the electron comes in here and pshoo, it shoots through. Copper doesn't care. Copper thinks, well, whatever, just as long as I have enough electrons, I don't care where they came from. But not tungsten. Tungsten's very fussy about its electrons. So when electrons come in to a filament that are being pushed from an electric current, they kind of bang around a little more. Oops, pardon me, excuse me, where are you going? Oh, excuse me, pardon me. And when they bang around, they cause these tungsten atoms to begin to jiggle and vibrate. They begin to jiggle and wiggle more vigorously because of all the bumping around. And we know that when atoms jiggle and wiggle more, they get hotter, right? Heat is actually a description of how wiggly atoms are. So this electric current is pushing into these tungsten atoms. And rather than let the electricity wiggle its way through like copper does, tungsten sort of puts up a fight. We call it resistance. And it's because the electrons around tungsten are configured in a different form, and they're not as willing to move. And all this wiggling and jiggling creates a lot of heat. And I guess, if you think about it, what we're doing is we are wiggling and jiggling all the electrons of the tungsten atoms, which causes ripples in the electromagnetic field. Now, if we wiggle and jiggle them a little bit, they'll make radio waves, maybe, or they might make microwaves. Or if we wiggle them and jiggle them the right way, they might make infrared waves, which are heat. And the filament begins to get hot. But what if we wiggle them and jiggle them enough so that they are now wiggling and jiggling enough that the ripples they produce are actually red, orange, yellow, green, blue, and violet? We can turn this heat into light simply by taking the infrared wiggles and giving them a little more energy, which means more electrons, more electricity shooting in there, wiggle them a little faster to increase their frequency, and we get a higher frequency wave, and now we can make light that we can see. So that's how a light bulb works. The energy is wiggling and jiggling the atoms in the filament of the light bulb so much that their wiggles are fast enough that they match the wiggles of red, orange, yellow, green, blue, and violet light. And we see that because our eyes are able to detect those particular ripples. So we can make light if we make things hot enough. So heat, right? Moving electrons in electricity makes sort of light that we can't see, but heat can make light that we can see. An easy way to see this is if you take a piece of iron, which is sort of black, and of course it doesn't give off any light, right? If you turn the lights out, you don't even see it. And you put it in a fire. There's some flames, right? And the fire burns. And what happens is heat makes the atoms of iron start to jiggle and wiggle. And they make ripples in the electromagnetic field, but not ripples you can see. When we look at the ripples here, what we have to remember is the most energetic are the little ones, right? So at first, when it's not very hot, it's going to give off maybe some radio waves. In fact, if you heated up a piece of iron a little bit, and you had a very sensitive kind of radio, and you put it near there, the radio might start to go and make staticky noises, because this is giving off ripples that the radio could pick up. It would have to be a very sensitive radio. But it's possible to build a machine that could do that. We can't see that though. So we heat it up more. We add more energy. That makes the light, that makes the electrons jiggle more vigorously, which means they jiggle in a faster way. So here's a slow jiggle, Here's a faster jiggle. Well, if you jiggle faster, you get a higher frequency, a shorter wavelength, remember? And that changes you from a radio wave into a microwave. And if you add more energy and more heat, that will cause you to vigorously shake even more, which will turn you into an infrared. And then we would start to be able to feel the warmth coming off of this rod. If you took the fire away, you could put your hand near there and say, oh, it's getting hot. You'd feel the infrared through your skin. But if you keep adding more, guess what happens? You change the infrared waves into more energetic red and orange waves. And this begins to glow red hot. And then if you take it away and turn off the lights, it's now giving off light that we can see, orange and red light. And if you heat it even more, it'll start to make orange and red and yellow and green, and it'll start to look, when you mix all the colors, it starts to look white. We say it's white hot because it's giving off that energy. And so basically, all we're doing is adding energy with heat, which makes the electrons go from a very gentle wiggle to a more vigorous wiggle, which is a more energetic wiggle, and that changes the size of the ripples they make. If they wiggle more vigorously, they make a more vigorous ripple. And that then changes the ray into something that our eyes can see. So heat is another way to do it. There's another way you can wiggle electrons. Chemical reactions, right? Chemical reactions, if we look at them in terms of their simplest sort of description, it's when one atom comes close to another atom and something happens. Well, what happens is the electrons around each atom change. They do something. They interact. Maybe one is given to the other and stolen, or one is put back, or one is sharing. When they come together, the arrangement of the electrons has to change to make them stick and do their chemistry. That's what chemistry is. Whatever kind of chemistry happens. So sometimes when things react, sometimes, not always, but sometimes, if the remember the electrons around an atom, remember when we first learned about the atom way back? We learned that they had energy levels. We drew these pictures, right? 2, 8, remember 1s and 2s and p. Those were describing the energy of the electrons. Well, if these electrons move from one level to the other because there's a bond happening or something is changing, any kind of movement will produce ripples in the electromagnetic field. And sometimes they will be ripples that we can see. Sometimes they will be ripples we can't see. Many chemical reactions produce infrared ripples, which are heat. Many produce light. The chemical reaction of burning, of fire, right? When you combust something, combustion, which is taking a fuel, like something like methane, and combining it with oxygen, gas, and you get CO2 plus water, H2O, right? Well, this also produces the shaking of electrons. When the electrons shift around to go from these reactants to turn into these products, they change their position. And in doing so, they make ripples. Some of the ripples are infrared ripples that we feel the heat of the fire, and some of them are actually vigorous enough that they give us the reddy-orange glow of the fire that we see. So chemical reactions can wiggle electrons, can't they? So they can produce different waves of light. Lots of animals use chemical reactions to produce light, like a firefly, for instance. That's what it does. Right? This has a fancy name. It's called chemiluminescence. It's a great big word. Chemiluminescence. This just means light, and this means light from a chemical reaction. Chemiluminescence. Right? When it happens to living things, we call it bioluminescence. We like to give everything a name, even though they're really all the same thing. We just like to give them all fancy names. So a firefly or a glowworm, many marine animals can produce glowing in their bodies by chemical reactions. Here's an interesting thing. Some of you might be looking up at the ceiling and you see the fluorescent light. So here, I'll give you an example of a fluorescent light here. a fluorescent light bulb, it doesn't work like the one we described before, where you have the filament of tungsten and you push the electrons through and they get hot. It works differently. So it's a tube, a glass tube. And the glass tube is connected to electricity on both sides, so that electricity can flow through it. So the electrons are pushing their way around this wire into the tube, like this. Now the tube has inside of it mercury atoms, or ions. Mercury gas, basically. We call it mercury vapor. And of course, mercury has electrons around it doing their thing. When the electrons shoot through here, they smash into the mercury atoms, and they cause the mercury atoms' electrons to wiggle and shake, which produces an electromagnetic wave. But it produces a wave of ultraviolet. We can't see that. So the ultraviolet wave shoots off of these atoms as the electrons crash into them. But we can't see that. But we're very clever. We've learned that there are certain molecules, typically molecules with phosphorus in them, that do something cool. If ultraviolet light hits phosphorus, it will then wiggle differently. Its electrons will shake and wiggle. But they will now produce a wave of visible white light, or the colors that we can see. So we coat the inside of the tube with a phosphorus chemical. That's why these tubes look whitish when you look at them. They're not clear. If they were clear, they wouldn't work. So when these little ultraviolet rays that are being produced by the mercury hit the phosphorus turns them into rays of light that are visible to humans. They are in the range of the red, orange, yellow, green, and blue. And they light up the room for us. So it's a very clever way to wiggle electrons in such a way that we can produce different waves of light and change them from one to the other. And that's essentially what happens inside this fluorescent tube, or this fluorescent light bulb. So fluorescence is a word we use to describe chemicals that will give off visible light if you wiggle them with another kind of light that you can't see, usually ultraviolet or something like that. Okay? So there's lots of different ways to wiggle electrons. And any kind of situation where you wiggle one is going to produce a wave or a ripple in the electromagnetic field. And so you could probably think of more. There's lots of things. Primarily, though, we do it in a couple of ways. We do it with electricity and heat most of the time. A little bit of fluorescence too, but more often we use fluorescence for, fancy little stickers in your books or stick on your wall. But of course, the fluorescent light bulb is everywhere. It's very useful. And the nice thing about it is it uses less energy than the electrical light bulb that has to use a filament and use a lot of heat. These bulbs do not get very hot because they don't produce very much of the infrared ripples, because it's a different system, different setup. Whereas the old light bulb, the tungsten light bulb that I described way back in the video, it produces a lot of infrared, which is hot. And we really don't want hot. We're trying to make light, so it's not as good, right? Our energy is being sort of wasted as infrared rays instead of the visible rays that we can see. Now that we've talked about how we can make light, we should talk about how the eye can see light. So inside your eye, if we take a look at an eyeball, like this, your eyeball has a hole right here. It looks black because it's dark in there. It's like looking into a cave. So when you look at someone's eye, there is no light streaming out. So the inside of the eye looks black. So the pupil of the eye is basically just a hole that looks right into your eye. But you can't see anything because there's no lights on in there. So it looks like a black spot, but it's really just a hole. Around that hole is a sort of area called the iris, right? This is kind of a cross section, so I'll just draw it on the top and the bottom. And that's the colored part of your eye. It could be blue, it could be brown, it could be hazily green or gray, and there's all different shades, right? And that's basically a big muscle that can squeeze like a sphincter to open and close that hole to get it wider when it's dark outside, so more light can go in your eye, or to make it smaller when it's really bright, because you don't need that much light. And inside the eye here, you have a lens. And we don't really know much about lenses yet, but we're going to learn what they do. They allow us to focus and bend light to make pictures. But we don't need to worry about that. On the back of the eye is a membrane called the retina. And this retina is made up of special cells, special nerve cells, that are all connected to each other in a big sort of like cable. They all have it's very hard to draw, but all of these cells are connected. You can imagine millions of little tiny nerves making up this giant cable, which is called the optic nerve. It's many different channels all wound together, like a big wire with many wires inside. So that's the optic nerve. And of course, it goes to your brain. That's how this is to brain. That's where it goes. And on this retina, there are 3 different kinds of cells. Actually, there are 4 different kinds of cells. There are little cells that are sort of shaped like this under a microscope. So we call them rod cells. They look like little rods. And there are others that are sort of shaped a little bit more like this. So we call them cone cells from their shape. And they're all along the retina, millions of them. Now, the rod cells will be activated. So what that means is if a ripple comes through your eye, remember, it's just a ripple. If it hits the retina, then just like the cork in the water would start bobbing if a wave hit it, the molecules inside the rod cells will begin to bob. They'll begin to shake and move because these waves are hitting them. And when they shake and move, they trigger a nerve signal, a complicated process of ions flowing across the nerve membranes, which makes what we call a signal, which shoots to the brain and tells the brain you're seeing something. But the rod cells are only sensitive to whether or not there's a ripple or not. They can't really tell the difference between different sizes of ripples. So rod cells basically don't tell us anything about what color the light is. They're basically black and white. In other words, they have the ability to light up, or send a signal, I should say, when light hits them, but they can't tell the difference, whether it's green or blue or yellow. It's just something that's light. So it would be sort of it basically tells us there's something there, but it doesn't tell us much about the color. Whereas the cone cells come in 3 different kinds. There's what we call red ones, green ones, and blue ones. Now, where else have you seen red, green, and blue? For short, RGB. If you know anything about television screens or computer monitors, you often see RGB because these screens and monitors are made of 3 different colors, red, green, and blue. And in fact, what's weird is that's the only colors you will find on a computer or a TV, are red, green, and blue. And you're saying, well, wait a minute, sir, I watch television and I see many different colors. Well, that is going to be one of our future lessons, and that's going to be an interesting one too. But all we really need for humans to see all the colors we see is red, green, and blue. So what this means is the red cone cells will only wiggle if the wiggle is the size of red light. The green ones will just not even bother to wiggle on that. So if red light comes into the eye, all of the red cone cells, their molecules inside will begin to feel that, like the cork bobbing on the ocean, and they will wiggle and set off a nerve signal that tells the brain, you're looking at red stuff. You're looking at something that's red. And if another wiggle comes in that's a little bit more energetic, right? because it's got, remember on our picture, it's got shorter wavelengths. Only the cells, the cone cells that are green, those molecules will begin to wiggle and jiggle. The red ones will not, the blue ones will not, and your brain will get a signal saying you're looking at something green. And if a really energetic one comes in, blue is even more energetic, right? It's got a higher frequency, shorter wavelength, more energetic. It will wiggle only the blue cone cells, and your brain will get a message that you're looking at something blue. So you have 3 different kinds of color-tuned receptor cells that wiggle for only those waves. They will not wiggle for infrared. They will not wiggle for ultraviolet. They will not wiggle for radio waves. They will only wiggle for red, green, or blue light. And that's how your brain can tell what color you're looking at. You'll have to wait to find out how we see things like yellow and orange and other colors too. But there is a way, and it's done by all these 3 cells sort of working together. All right, so that's how you get light, right? There's different ways, different fancy names for it. But essentially, all of the ways of getting light come down to one thing: wiggling charged particles. And that's what makes the waves that we call electromagnetic radiation. And remember, only a small piece of it is what we can see. The rest of it is pretty much undetectable to humans. Interestingly enough, though, some animals can detect things that we can't. So just for fun, rattlesnakes, here's a rattlesnake head. Big eye here, little mouth that sticks out with his forked tongue, right? The rattlesnake has tiny little receptors in the front of here. It's not his nose. You might think it's his nose, but it's not. Inside there, when infrared waves are being made by something, if they go in there, now remember, what's infrared? Heat. So things that are warm are making these ripples. And when they go into these little receptors, it sends a message to the brain. So the rattlesnake can detect heat, not just like we do by feeling a warm campfire. They could be where I am, and they could detect the heat of your body. I can't feel the heat coming off your bodies. I'm not sensitive enough for that. But the rattlesnake's receptors can find heat. And so this is in the pitch black, they would know where you were because they would sense the heat from your body. It's very similar to the way the military uses infrared cameras. You might have seen them on TV where they can see the glowing blobby heat of a person, right? They take the heat, they turn it into a visible picture so that we can see it, but it's really just heat. And so the rattlesnake can detect infrared much better than we can. So well that it can probably in its brain develop a picture just based on the heat that a little mouse or some prey is giving off. Sharks can sense all kinds of electromagnetic radiation. Sharks, in their mouth or in their nose part, have a whole bunch of tiny little pits all over the nose of a shark. If you look, look up close, you'll see all these little dots. They kind of look like maybe hair is going to grow out of them or something, like little pores, but not hair. These are sensors, and they can sense some of the electromagnetic radiation that comes off of a person. Because remember, inside of you, chemical reactions are happening all the time. And when chemical reactions happen, electrons wiggle. So your chemistry is producing light all the time, but it's producing light that we can't see. The ripples are the wrong size. Maybe they're radio waves or microwaves, but the shark can sense them. Those waves, even though they don't affect our body, these cells in the shark are sensitive enough so that even in the darkest, muddiest water, the shark can find things because it can sense the ripples coming from the chemistry inside a living thing. Pretty cool. So some animals can actually detect parts of the spectrum, parts of the light spectrum that we can't. We can see red, orange, yellow, green, blue, violet, and we can feel a bit of heat. That's it. That's all we can do. We can't tune into Yes FM in our head. We can't really, I mean, we do get a sunburn, but we don't know it. It's always after the fact. We can't sense and see, oh, I feel the sun, it's burning. Well, it's just after, right? You get sore, your sore skin, it's already done. It's usually like a couple hours after the sun hits you. So all we can sense are these limited parts of the spectrum. But other animals can sense a few. Bumblebees can see ultraviolet light. Ultraviolet light, we can't see it. Bumblebees can. And in fact, we did a cool thing. We looked at flowers. So typically, here's a flower, right? It's got nice red petals, let's say. And maybe it's got a little yellow center. And that's what it looks like to us, right? But of course, in the center is where the nectar is. That's where bees want to go. And so what we decided to do as a fun experiment was shine ultraviolet light on flowers. And not our eyes can't see it, but we can build a machine that can see it and tell us what it looks like. So the machine showed that the flower had weird patterns like this that showed up in ultraviolet light. And these patterns were almost like sort of like a bullseye saying, over here. And bees, of course, can see these patterns. So when they fly up to a flower, they see the petals and the colors, but they also see sort of a pattern that kind of points them into the middle of the flower where they can find the nectar. We don't see that, but bees do, because they can sense the ultraviolet ripples that make those patterns. So there's lots of things out there that humans can't detect, right? But other animals can. So that's kind of interesting as well. So remember, wiggling a charged particle makes ripples in the electromagnetic field. And there are many ways to make electrons or other charged particles wiggle, but all of them produce ripples. And we can use the ripples for all kinds of different purposes. Okay, we'll stop there for today.